All right, so what we're going to do is we're going to add our second major conservation law. So we've been playing with conservation of energy for a while. Now we're going to come back and talk about conservation of momentum. To set this up, let's start by talking about what a system is. So up until now, basically we've been able to treat pretty much anything that we've been working with as if it were a particle. And so that's going to start to change as we go forward. And so the first thing let's do is let's talk about a system. And a system is just a fancy way of saying we've got a collection of particles. So here you notice that we happen to have a 3-particle system. It looks like I've got 3 sort of identical particles here. Now, of course, I can have more than 3 particles and still just define these 3 particles as my system. So part of what we're doing when we're saying that we have a system is we're basically just sort of partitioning off, right, fencing off, here's the group that we care about as the system. There may be other stuff out there, but that's not part of the system. And in fact, the name that we'll end up giving this is we'll talk about anything else that's not inside our little red box here as the environment. So we've got a system, and that system is within some environment. And so if I want to think about forces that can act on the pieces within my system, well, there may be some force here that we see that, again, thinking about our label. So this is some force felt by mass 1, by particle 1, exerted by particle 3. Okay? And interestingly enough, that's an internal force. And internal forces are basically forces that one member of the system exerts on another. So since both particle 1 and particle 3 are inside the system, this is an internal force. We might have another force that say here where particle 1 gets pulled on by particle 4. And the difference here is that particle 4 is not within our system. And so that's an external force. And external forces are forces exerted by something outside the system on something inside the system. So we'll see in a second why these things matter. But we have one thing we can do with our forces is break them up into all the internal forces and all the external forces. All right. So let's come back to the conservation law that we've been dealing with real quickly and think about conservation of energy and let that sort of help set up how we want to think about conservation of momentum. So the first question becomes, when's the energy of a system conserved? So we've seen conservation of energy problems where, say, we've had 2 blocks connected by a string, and so we wanted to talk about when is the energy of that system conserved, that 2-block system. Well, all the energy conservation tells us is that the energy you started with has got to be the same as the energy you finish with. And for that to be true, that means that the work done by non-conservative forces has got to be 0. So we know that energy is conserved when the work done by non-conservative forces on your system is 0. So when is it that non-conservative forces do no work? So our definition, we said, hey, as long as we got a constant non-conservative force, and that's basically the only type that we've really worried about playing with this semester. So if we've got a constant non-conservative force, then I can calculate the work done by any constant force to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between these 2 vectors. And so there are 3 different ways that I can have 0 work done by non-conservative forces. The first is simply to have no non-conservative forces, right? If there are no non-conservative forces, then certainly they do no work. The second is I can have non-conservative forces, but there's no displacement. So this would be another situation in which the work done by non-conservative forces is 0. And the third case is a situation where I have non-conservative forces. My object that those non-conservative forces act on is being displaced, but the angle between the non-conservative forces, the vectors of the non-conservative forces and the displacement is 90 degrees. So when non-conservative forces are perpendicular to displacements, they do no work. And of course, the one we've seen most often with that situation is the normal. So let's think about momentum. So when is the momentum of a system conserved? Well, one of the things we talked about was the momentum impulse theorem, right? It tells us that the change in momentum is equal to the net impulse exerted on the system. So momentum is going to be conserved, is another way of saying that the momentum doesn't change, which is another way of saying that delta P here is 0. So for delta P to be 0, that means that the net impulse has to be 0. So if I've got a constant net force, that net impulse can be calculated by thinking about that constant net force times some time that it acts on that force. And what you notice here is, unlike with our work term, where there were a couple of different options for ways to make the work done by non-conservative forces 0, there's really only one way that you can make the net impulse be 0, and that's to have the net force be 0. So when is it that the net force is 0? Well, the net force is just, right, sometimes we write it this way, sometimes we write it this way, but either way we're writing it, we want this to be 0. And again, one of the things that we talked about is that I can break up the vector sum of all my forces into the vector sum of all the internal forces plus the vector sum of all the external forces. And the thing that's interesting about these internal forces is that if you think back to that internal force on our first diagram, where we said there's some force exerted by particle 3 on particle 1. Well, Newton's third law tells us, since for every action there's an equal and opposite reaction, says that for every force there's going to be a pair to that force that's going to be equal in magnitude, opposite in direction, the same type of force, but we've switched which forces or which object is causing the force and which object is feeling the force. That means that for every internal force, there is a pair to that internal force that's going to be equal in magnitude and opposite in direction. And so when you add them up, the vector sum is always going to be 0. So from Newton's third law, because of Newton's third law pairs, the sum of all the internal forces acting on our system is going to be 0. So to talk about the net force, the only thing that's really left over is just thinking about the vector sum of all the external forces acting on our system. So what this tells us is that the momentum of a system is conserved when the vector sum of the external forces acting on the system is 0. So we most often are going to take advantage of this when thinking about collisions. So a collision is a brief, intense interaction between objects, right? That's sort of our physics definition for it. And why that's important is because the brief tells us that it happens during a short amount of time. The intense tells us that basically the forces between the objects that are colliding are going to be much larger than any external forces that happen to be present. So effectively, we can always conserve momentum for collisions because over that brief period of time the collision's occurring, the only thing that we really need to worry about are those internal forces between the objects in our system. And we know that they're going to cancel out. So this means that momentum is always conserved for a collision. So the initial linear momentum of our system is going to be equal to the final linear momentum of our system. So let's say we've got a simple system with two objects. So here's mass 1 over here, here's mass 2. They're sliding towards each other. Again, I've drawn the free body diagram for both of these masses. And you notice that right now, the free body diagram for mass 1 is just the normal and the weight, and those two cancel out. The free body diagram for mass 2 is, again, its normal and its weight. Those two cancel out. So the net external force acting on my system is 0 because everything's canceling out here. They're going to slide towards each other. They're going to come into contact. And while they're in contact, then I'm going to get this internal pair of forces, this applied force that mass 2 exerts on mass 1, pushing it back to the left. This applied force that mass 1 exerts on mass 2, pushing it back to the right. But we know that these two forces, because they're internal forces, they're still going to cancel out. So the net force on my system is still 0. And so what that means is that those internal forces are now going to change the momentum of the individual masses, but the total momentum of my system is still going to be conserved. So my two masses will bounce away, right? Mass 1 go back to the left, mass 2, move back to the right. But the total momentum of my system is going to be conserved during this collision because the net external force acting on my system was always 0. So this gives me conservation of momentum. And so notice this is sort of our most general expression when we've got two objects. And the thing that we're going to need to pay attention to, because this is a vector equation, the first thing we're going to need to deal with is, well, how many dimensions do we need? So notice in this case it's just a one-dimensional problem. So we would just have a mass 1 v1 initial x component plus mass 2 v2 initial x components equal to mass 1 v1 final x component plus mass 2 v2 final x component. That would be our only equation. It would only be in the x direction. And now we would need to pick a positive direction and keep track of the signs. So if we said to the right was positive, then mass 1's initial velocity would be positive. Mass 2's initial velocity would be negative because it was initially moving to the left. After the collision, mass 1, now it's moving to the left, its final velocity would be negative. Mass 2 moving to the right's final velocity would be positive. So again, it's a vector problem, and we've got to work it like a vector problem. And so even when it's whether it's one-dimensional and we just keep track of signs, or it's two-dimensional and so we need to break everything up into components, however we need to deal with it, we've got to work it as a vector problem. So what types of collisions are we going to end up dealing with? And you'll notice there are basically sort of 4 types. The first one, the easiest one to recognize, is a totally inelastic collision. You know it's a totally inelastic collision because your two objects are going to stick together. So what happens is, let's say those two boxes on the previous screen were sliding towards each other and they stick together and then move off as a single object. That's going to be a totally inelastic collision. During a totally inelastic collision, you lose the most amount of energy possible. Right? So you're clearly losing energy, and in fact you're losing as much energy as you can because you need all that lost energy to go into getting your objects to stick together. So the only thing that's conserved during a totally inelastic collision is momentum. Partially inelastic collision is basically, well, you still lose energy, but now your objects don't stick together. So in the previous slide, basically what we watched, the way those objects bounced off each other but didn't have as much energy at the end as they did at the beginning, that's going to be a partially inelastic collision. So energy, you're losing energy, but momentum is still conserved. Elastic collisions. Well, elastic we recognize from our elastic potential energy. So basically what an elastic collision is it's the one special case where both momentum and energy are conserved. And so that and energy being conserved is basically telling you that as your objects collide, effectively they act like springs, store up all the energy as they come together, and then give you all that energy back as they push back away from each other and move apart. So elastic collisions are the special case and the only case where both momentum and energy are conserved. And basically you've got to be told that it's an elastic collision. So you got one of two choices. You can either be told it's an elastic collision and then you know you've got this extra conservation principle you can use, or if you're not told, the only way you could figure it out would be to calculate the kinetic energy at the end, compare it to the kinetic energy at the beginning, and if it happens to be the same, it means you had an elastic collision, but you couldn't solve for that using anything special about energy. And then the last option we're going to call superelastic collisions, and basically what this means is it's just a fancy way for saying that we've gained energy. So we know inelastic collisions lose energy, elastic collisions conserve energy, and so superelastic is just a way of saying that we're going to end up gaining energy. Again, momentum is going to be conserved because what's true in all collisions is that momentum is always conserved. And so one way that I might add energy is basically if I have two things collide, but maybe there's some spring that's compressed that as they collide is able to add that, it releases on the collision, and so it's able to add that additional energy during the collision. Or Another option is that maybe what I actually see is effectively a collision in reverse, or what you might think of as an explosion. So a superelastic collision where I've got more energy at the end often looks like a collision where you're running the movie backwards. So instead of two things coming and sticking together, maybe I have two things that are already stuck together and blow them apart. And so that, again, momentum is going to be conserved because the blowing them apart, those forces are all internal, right? The explosion comes from pieces within your system pushing away from each other, and those are all internal forces. So the net external force is still zero, so momentum is still going to be conserved in those situations. But now we're going to have much more energy at the end than we did at the beginning, so we've gained energy. So that's going to be one way of thinking about this type of superelastic collision. So these are the types that we're going to deal with when we come to class on Wednesday and Friday this week and basically work problems on conservation of momentum.